So this presentation is also going to be on the internet. And SK Planet will put a video up I learned, and the slides will be on SlideShares. So if you find interesting information on these slides that you want to look up later, you can always do that on the internet. So what we are doing is creating virtual worlds. And for what we are doing, we want to join film and game in a way where we cannot have sharded worlds like World of Warcraft, where you can have a friend playing in one server and another friend playing in another server, and playing avatars who can never meet. So what we are doing is something that automatically has to do with big data, and that automatically has to do with high-velocity databases. And that is the reason why, at a certain point, I went on a quest after a project that used Java and MySQL, and try to have a very objective look at what would be the best language and the best database for the next game server that I would be programming. What I came up with was VoltDB as a database and Erlang as a language. And these are both open source technologies that are built for scaling. And I would like now to look at what makes them special, how they look, what does the source look like if you program them, and to try to answer the question, or help you answer the question, if they make sense to use for you. VoltDB and Erlang actually have some things in common. They're both the results of a concrete need of a company that was in IT. They're both made for distribution. It is not like many other products that distribution was added later. They are made for multi-core, like we find now in all commodity servers. And they are both truly different approaches to solutions that we saw before. They are not only made for parallel architectures, but they're also using parallelism to be different and to solve things better than before. Both products have a strong company behind them that is also providing professional support. And both are quite well known in circles that have to do with the problems that they're dealing with, although not everybody knows VoltDB or Erlang. Let's start with looking at VoltDB. VoltDB, one could say, as a rough approximation, could be described as Redis plus SQL plus scale. From a business perspective, the reason to use VoltDB is quite clearly to reduce costs, to be able to scale seamlessly, as we learned this morning in the keynote, and to maintain strategic flexibility. The reason is that the way that data is stored in VoltDB is much less special than in many other databases that have come up in the new SQL times. If you look at it as a programmer, then the reasons are a little bit different. It's more like, okay, not everything about SQL was bad, so let's not throw all of it away with NoSQL databases. Still, you can use the goodness of in-memory that you have probably learned in Redis, and you are using a product where you can later, if you're successful, be sure that you can scale. I would like to describe VoltDB a little bit like the Redis of clusters. I think many of you know Redis probably, and Redis as an in-memory database can do stuff incredibly fast. Just probably it is never going to be a distributed database. There are efforts underway to do that, but the problems they are facing are probably such that Redis will not have transactions when it is run in the cluster. VoltDB, however, does have that. I would also like to compare VoltDB to MySQL. I think everybody here has probably used MySQL at one point or another. And however, the point can be made that SQL in itself has some flaws. In the end, it's about essentially math. It's about relational databases. And that means no matter what the syntax is, there's a lot of sense and a lot of science in how SQL works. And if you wouldn't have queries and only key value access, you might sorely be missing queries at some point. If we look at CAP, some of you might know it, that is a very good tool to get orientation about databases. Many NoSQL databases, for example, are sacrificing consistency and introducing eventual consistency and focusing on high availability and partition tolerance. To just get an orientation, VoltDB is rather on the side of consistency and high availability, even though you can make the point that VoltDB is not really lacking in partition tolerance, and there are some flames going on in the blogosphere about whether VoltDB can claim that it really satisfies all of CAP. ACID is something that is summing up attributes that everybody should probably assume are for granted in a database. Basically, ACID describes that if I store something into the database, at a later point I want to get the same thing back. One should think that's for granted, but it's not. Not even the Oracle default setting is giving you true ACID. MySQL, by the way, is a little better at that. And VoltDB is giving you ACID transactions. An interesting metaphor to think about your problem, whatever it might be, is double bookkeeping. And if I can take games as an example, if you have a very simple game where one player only basically does actions that never really affect another player, then you do not need double bookkeeping. But as soon as you have a game where one player can interact directly with another player, you have to have the possibility to do double bookkeeping. That means, for example, if one player sells a sword to another player, you want to be sure that in the end, the sword has changed hands and the money has changed hands. And do not have a situation where a transaction crashed and you have half of it realized, or have two swords all of a sudden, or no money anymore. If the database does not provide you with double bookkeeping, it is very, very hard to implement that on top of a database that does not provide it. So how does VoltDB manage to be so good? The magic sauce really comes down to compiled-in queries where you program stored procedures in Java that in the end become part of the database engine. Another ingredient that's very important is single-thread execution. I'll explain that in a minute. And the same with snowflakes and clones. What VoltDB does is not very much surprising. It does a consistent hash about the entirety of the data that has to be stored, and then stores the data across several servers. It even does that with added case safety. That means an individual server could crash, and you would still have all of your data. That means that, for example, if the left-hand server crashed, you can take the content from the server to its right-hand side and to the far right, and you would still have a complete copy of your entire data. What it then does is it uses the fact that most real-world data has a Snowflake structure. For example, you could have a customer table at the center of the snowflake where the primary key in red is the customer ID. Most of the data in your database would, in that case, point to the customer with their foreign keys. And if it's going down the structure, then you would have other tables that would have their own primary key that had other detailed tables that would be pointing to that dependent table. However, you also always have data that is not part of the snowflake. To stay in our example, for example, the product numbers and the table where you have the names of your products would probably not be part of the snowflake, but in a parallel order. What VoltDB does, it is sharding the snowflakes across all of its servers. And for example, if the hash in a very primitive solution would go on the surname of the customers, then the first server would be storing all of the customers that have A, B, or C as the first letter of their surname. The data that is not part of the Snowflake structure is then cloned by VoltDB and replicated across all servers. And that's a very important, a very genius trick that they're using there. And it makes sure that most transactions you want to do can be done on a single server in a single thread, because you have most of the data available that you would use in most of the transactions that a normal business operation takes. VoltDB is organized in a way that every partition of the data is governed by one thread. One thread, obviously, cannot be in contention with itself. It means it does not need locks against itself. So if you have one thread executing one transaction, that basically means you can have transactions without locks. This is true for each of the individual partitions inside VoltDB, and this is one important key why it can be so fast. I made a benchmark a couple of months ago with VoltDB 2.5 and a Node.js driver that VoltDB Inc. has produced. I used a 96-core VoltDB cluster on the EC2 and 64 cores Node.js clusters as clients. What I came up with were 695,000 transactions per second. Each of these transactions had 4 operations, and that made for almost 3 million operations per second. The important number maybe in this context is the 12,500 transactions per second that could be measured per node, which gives you an idea how you can scale just by dividing your requirements by this number. So you end up having the number of cores that you probably need. The benchmark was a very simple situation, a TV contest where many callers can call in and vote for a candidate in a TV show. This is the structure of the database. It's very unsurprising. You have a table with contestants, you have a table with voters, and a table with area codes that adds a little bit of flavor to the problem. These are the 4 operations that made up the transactions. Basically, it is a lookup whether a contestant number is valid. Then it's a lookup over the phone number of the voter and a count. That counts if a voter has voted more than once. Then the area code is looked up. And finally, the vote is inserted into the database. VoltDB comes with drivers for a lot of languages, and that list might not even be complete at this point. And to sum it up, VoltDB is, in my view, for a lot of applications that in the moment MySQL is used for, and a lot of applications that in the moment maybe NoSQL databases are used for, a better choice. Mike Stonebreaker, who basically invented VoltDB and founded the company, famously a couple of months ago said that all problems that Facebook faced while growing with MySQL could have been solved with VoltDB. There are a lot of people who are laughing about this, but I believe in a certain sense he's probably right. Getting started with VoltDB is easy. You can download VoltDB from voltdb.com. They have a very elaborate getting started section inside the installation. You can run a Hello World program locally on one computer to get your toes wet. I always recommend to read the original MIT paper that kicked VoltDB off, and there are very good webinars on the VoltDB website. I have looked at 14 databases, more or less in the light of what is best for games. And there's an upcoming blog post. And if you would like to learn when it comes up, I invite you to join me on Twitter at @Diedrich. So the next part of my talk is going to be about Erlang, the language. And I like to sum up Erlang that it could be to Java what Java was to C++. One of the most prominent improvements of Java over C++ was that they abandoned pointers and introduced references instead. In the same way, I like to say that Erlang allows you to overcome deadlocks that are very easy to be made with Java. When I showed a presentation like this to Joe Armstrong, the inventor of Erlang, he said I should cut it because Erlang is so much more. Again, from a business perspective, looking at Erlang, probably the most important argument for it is cost. Erlang is also very likely to reduce your downtimes because it is famous for having hot upgrades, and because Erlang is very productive and is very fast to program, it is probably likely to shorten your time to market. From a production perspective, you can also look forward to need a lot less hardware. For example, the game company Wooga boasts that they replaced 200 PHP servers with only a handful of Erlang servers. And another characteristic of Erlang is that you tend to make fewer errors while programming it compared to other programming languages. Who's using Erlang? One of the inventors of Erlang, Mike Williams, said you're probably using Erlang all the time without realizing it because it is used in telecom. And whenever you pick up the phone, you might be using it without knowing it. In the games sector, a lot of well-known companies, especially in the web games, are now using Erlang to program their game servers. The poster child for Erlang is Klarna, which is a financial services company who is giving services to e-commerce sites for 12,000 e-commerce sites. And they are saying that they had 30 seconds downtime in 3 years thanks to using Erlang. Also, many of the more well-known distributed databases are using Erlang in part for glue code or are programmed in Erlang entirely. Among them, Membase, that is Zynga's database, for example, for Farmville, Riak, or Big Couch. The sweet spot of Erlang are stateful servers with high throughput. What the game company Wooga did when they replaced 200 PHP servers was most of all that they started to hold state in the server instead of going to the database for every single session request, reading the data from the database, handling the request, and sending the result back. For example, in the case of Membase, Erlang is used as cluster distribution layer that is handling the cluster logic itself, while the actually data lifting is left to C or C++ code. Erlang is also famous for having been used for the Facebook chats. Chats are pretty hard to program, and Erlang is pretty good at doing that. The origins of Erlang are at Ericsson. That is a telephone company in Sweden. And the name of Erlang is also deriving from Ericsson language, probably. Ericsson makes billions programming telephone switches. So that is serious business. And a long time ago, they had started to program their own language for that, and that was called Plex. And that worked pretty well. The only problem it had was that it took too long to program products with it. So in the 80s, the computer science lab at Ericsson was tasked in making a better Plex. And if you think about it, in the 80s, or earlier even, C++ was also developed at a telecom company, AT&T. So Erlang was built along the lines of what Plex could already do. It should be very reliable, it should be very good to maintain, it should be good at distribution, but it should also be highly productive. How this was achieved in the case of Erlang was by microprocessors, which are not system processes, but something that the Erlang virtual machine offers you that has a very small footprint, is very fast to create, and in fact in Erlang it's no fun and it's no program really in Erlang if you don't create thousands of processes. A second feature of Erlang is pattern matching. Pattern matching is something that has nothing to do in this case with your regular expression pattern matching for string parsing, and I'll explain it in a second. Another feature are immutable variables. Those are variables that cannot change their content once they are set. To learn Erlang, you have to learn to think Erlang, and that can take some time. The language itself is learned very quickly. It is a short, small language, but to really think Erlang, you have to learn a couple of concepts, and we are going to look at them now. First, Erlang is not object-oriented. It almost is, but not quite. The actor model is what Erlang is using, and that is also around since quite some time now. It also has behavior. It also joins data and code, but it adds to it a process. And this process is part of the actor. The benefits of the actor model are said to be that it can be used much better to model the real world, because the real world is parallel. In the real world, we have a lot of actors who send each other messages, but do not stop to act until they have an answer back. And this is the great difference of the actor model as opposed to object-oriented models. This is also the first piece of code I'm introducing here. PID, exclamation mark, MSG, in Erlang means send the message to the process of process ID PID. Thinking processes has to be learned. It's not that easy. And the main pillars to think about is that processes don't share state. They do not reference each other's data. They only send each other copies of their own state. They always communicate asynchronously and do not wait for an answer. So what you have as a method call in object-oriented programming is exactly the opposite of how actors communicate with each other. It's very important to always remember that processes are very cheap to create and keep. So what you want to do is to have a program that consists of thousands of processes. I would like to compare Erlang at this point to object-oriented objects and threads in, for example, Java. If you look at the black arrows, those are to signify threads. The blue bubbles are objects. A couple of objects kind of inhabit a thread. In Erlang, you have actors, and those actors are processes, and every actor is its own process. In object-oriented languages, the objects have a certain lifetime, and after that lifetime, they are terminated and destroyed, and this does not affect the thread. So you have the concept of idle threads, which are signified here with those blue squares. Usually you want to reuse threads that are idle because they cost a lot to create. When you do that, you run into a new host of problems because sometimes it can happen that an object survives too long into the next phase where a thread is reused. Or an object is destroyed too early while another object still wanted to access it. In Erlang, this problem does not exist, because obviously each actor is its own process. If one of them dies, which happens all the time, in fact, letting actors die is the error handling concept in Erlang. The actor is simply restarted. In object-oriented languages, state is referenced across threads and objects. And that leads to the situation that errors propagate along the lines of these references. And objects need locks. If you have a resource that is content, you have to have a mechanism that makes sure that one change is not overwritten by another change. These locks, again, can stall and can cause problems. Processes have a way to be transactional, and it is the way to avoid locks in Erlang, to delegate a certain type of problem to a certain individual actor who's then going to take care of that state and that state alone. And because that one actor is one process, it cannot raise itself. And because it cannot raise itself, it creates a funnel where lockless access to one resource can be realized. Thinking parallel is the most difficult part of learning Erlang. On the other hand, it is not only Erlang where you have to think parallel, but every of the new architectures that you're confronting in hardware will require that of you. Thinking parallel means to give up certain securities and guarantees that as a programmer you wish they were there. For example, the general problem is a problem where you have two armies in a metaphor attacking one city, and two generals who have to have an agreement on what time they want to attack that city. To find out that they are on the same page, one general can send a messenger to the other general. And so that the first general knows that the messenger indeed reached the second general can send a messenger back. And to be very sure on the part of the first general that the second general knows that the first general got the acknowledgement of the first messenger, he can send a messenger back. Unfortunately, this can go on ad infinitum, and it doesn't help. The messenger could get lost at any time, and even the generals could get lost, so that not receiving an answer could mean the other army doesn't even exist anymore. What this means, if you think about it, is that you can never have security that in two different processes you have an agreement about state. And that has very grave consequences and is not very nice. It's not a problem for Erlang, it's a problem you're confronted with whenever you program in parallel architectures. Another concept that helps a lot programming in Erlang is to give up that you would ever know at what concrete time something happened, but would go back and be satisfied with knowing in what order things happened. The next chapter is thinking functional. In Erlang, you have the situation that you have small functions and immutable variables. And that leads to the situation that you try to avoid to store results in a variable at all. Rather, you have very small functions that call other functions and return the result immediately. A very important feature of functional programming is that you have a lot, if not the complete state, in plain sight. That can sometimes be very awful if you have to update just one data point in a complex structure, but it is very nice for debugging and maintenance. This is an advantage that you only understand after programming Erlang for some month. But at that point, you realize what the real productivity and maintenance friendliness of Erlang means. Immutable variables, as I pointed out, mean that you can never change the value in a variable once you assigned it. You always have to write the name of a second variable, for example b, if you want to have a new value stored. This prevents a whole class of coding errors. Obviously, it prevents the kind of error where you still think you have a certain value in a variable, while in reality, you have another variable value stored into it. Pattern matching is another very important feature of Erlang. This line of code can mean two things. The expected meaning is that the result of function is stored into A. It can also, however, mean that in the case that A has already a value assigned, the result of func is compared to A. And if the resulting comparison does not match, then the process crashes. The normal case that this is used is something like this. On the left-hand side, you have a tuple that contains a constant, OK, and a variable that is still empty, A. And what this line of code does is that it is at the same time asserts that what comes back from function has as its first element OK, otherwise this line crashes. And as its second value, it can deliver back whatever it wants. It can be a very complex structure, and that is stored into A. This makes Erlang source very different from normal source in, say, Lua or C or Java, and is also the reason why Erlang can probably never be changed to look more like the elegance of Lua does. Finally, let it crash is the concept of how you deal with errors in Erlang. This means that in the case that something doesn't work, you simply let the process crash. This is very hard to get used to. It means that you write no defensive code, which makes your programs be shorter and much more elegant and much more readable. Erlang comes with structures that help you to restart processes in a sensible way. Overall, it leads to shorter and cleaner code, and it has the beauty that it also handles all those errors that you never thought about. Finally, let's look at the syntax of Erlang real quick. How does it look like? The syntax of Erlang is very stable, and it's very small. It has not really been changed for almost 20 years. It can be learned really quick, within 1 week, because it's really not much. And it looks very declarative. This is a Fibonacci function, and obviously it looks a lot like the math explanation of it. This is a hello world example. The first 2 lines obviously are some instructions for the module. Then you have a function head start, and then you have the actual output to screen of hello world. This is a version of hello world that is more like a typical Erlang program, where you are using a process creation. Let's look at this for a moment. This is where it all starts. This is where it should go and print on the screen. This spawn function actually spawns a new process, and this new process starts at the head of the loop function. The loop function, the new process, enters its receive block and waits for a message. The main thread, the main process, is sending the message hello. Hello is received in the receive block of the second process. By the way, this is pattern matching again, because hello is an atom and matched in the receive block. A typical feature of Erlang is tail recursion, where a loop is created by a function calling itself, and the virtual machine taking care that the stack is not blown up. Erlang has been shown to be 3 to 7 times shorter in code than C++. A study by Motorola, done in 2002 to 2006, consisted of programs being programmed in Erlang and in C++. And the results were that Erlang is also 2 times higher in throughput and 3 times better in latency than the equivalent C++ implementations. Learning Erlang is quite easy using the web. I recommend scouring postmortems of successful Erlang projects, using Erlang.org to download Erlang, and refer to the resources that I'm listing here. Finally, Erlang Vault is our contribution to this ecosystem. It is the Erlang driver for VoltDB. It is open source. It exists as a stable synchronous version. And very soon we're going to have an asynchronous version posted on GitHub. This is how it looks. This is an insert call into a database and a select call out of the database. Here are some resources that you can refer to if you download the slides from the internet. And I mentioned that I have upcoming the Erlang Vault 2, that is an asynchronous Erlang Vault driver, and a blog post about databases seen with an angle from games. If you have any questions, I'm happy to also answer them by email. Just send me an email, and I'll be happy to come back and answer them. And probably we have questions and answer time outside in the lobby. Thank you very much.